Hello, hello. So we are moving on to the fundamental theorem of algebra, dissertation by Euler in 1799. So you're thinking about writing a math paper. I'm sorry, this one's already taken, so you might have to do something else. It seems simple, so we're only going to look at it the simple way. If we get a polynomial degree n, we should expect n zeros. They all should be written or can be written in terms of a plus bi, and they can be repeated. So if you have x minus 2 cubed, that's saying that 2 is a root, but it's kind of a multiplicity of 3. So that's all there is to it. Let's move on. There's 5 bullet points in the book, and I rearranged them because I think this is the most important thing that you're going to bring out of it. And that is, if you're told that p plus qi is a root or a zero of the polynomial or root of the, and I emphasize a real polynomial. A real polynomial, all the coefficients are real numbers. There's no i's in front of the variables. Then immediately you can say that the complex conjugate is also a root. All right. So when you line up all these linear factors, and you have x minus the quantity p plus qi and x minus quantity p minus qi, when you multiply all those together, you're going to have to multiply those together, you're going to have to add them and so forth. Remember that when you multiply this times this, you get a real number. And when you add them, you also get a real number. So in other words, when you multiply all those linear factors, you're going to get this polynomial. The i's are all going to cancel out, and that's why you have to have complex conjugates in there. So if 3 minus 7i is root, then 3 plus 7i. And this needs to be automatic. Okay, all these problems that you'll run into, if you don't see that right away, you have no chance of doing the rest of the problem. All right, the second thought, and I split them up to give you a few little examples as we went. Every real polynomial of degree n, complex linear factors. What does that mean? Well, it just means I can write it like this, or it might be I have 1 squared and 1 to the first power. Maybe I have complex roots and they're written like that, or maybe a repeated root. So that's what that one means. Oh boy, love it when that happens. All right, so if I just go slowly drag, maybe that's it. All right, every real polynomial product of real linear and real irreducible quadratic factors. So what does that mean? Well, remember that this delta stands for the discriminant of the quadratic. Woo! All right, so obviously b squared minus 4ac is something you've seen before. It's under the square root in the quadratic formula. So if we boil something down to a quadratic formula, we can find its roots. Well, we got problems when that's less than 0. Well, not problems. It just becomes a little more complex. Okay. All right, so we can leave it just like that. So if we have this as our linear factors, this is not, that's not real. It's got some complex numbers as coefficients. So what we'll do here is we'll multiply those two together to get this, and we create an irreducible real quadratic. Okay, so it's all about vocabulary here. They'll tell you, can you reduce this 5th degree polynomial into the real linear and real irreducible quadratics. That's what they mean. Do not keep going. Boo. Okay. Okay, nice and easy. That one is just the fundamental theorem of algebra, kind of restated. Okay. Nice and easy. The last one is, hey, if we have an odd degree, we know that sucker's going to cross the x-axis. And I think you played with this a little bit in calculus. So What's nice about that? Well, if we graph it with our graphing technology, we know we'll find at least one root. And maybe just with that one root, we can use like synthetic division and reduce that down and see some other cool stuff. So that's the thought. All right, so I'm just going to do a bunch of examples here. You can fast forward them. It's mostly getting used to the vocabulary. So if 2 minus 3i is 0, I stop in my brain. I say, oh, 2 plus 3i is a root. That's, automatic. So we have this crazy looking cubic. I know there's no z squared. You don't really say there's no z squared. I know the coefficient of z squared is equal to 0. A little distinction there. And we know p and q are real. That means if 2 minus 3i is a root, then 2 plus 3i has to be a root. So they tell you a lot. This is a level 2, 3, 4 problem. They kind of tell you how to do it. Part A, well, we kind of know that these are the linear factors, and therefore if we multiply those together, you're going to get this quadratic. Okay. We just came off a section that had comparing coefficients, and they skip a lot of steps. I don't. I like to write them all out. So I know this is quadratic times a linear. This is the most basic linear I can get. I really know what a is. I'm pretty smart, and I can see that z squared times az equals z cubed, but I'm trying to keep it open for you. When we compare a z squared, now notice I didn't multiply this out, and I want to kind of push you to do this the same thing. If I'm doing z squared here, what I'm thinking about is what would I multiply up here so I would get a z squared? Well, z squared times b would give me a z squared, and 4z times the az would also give me a z squared, and 13, no, there's nothing. So I go over here and there's 0. So I pull the coefficients and I get my b equal to 4. All right. Now let's look at the z. What would I multiply here to get a z? Well, z squared's out. 4z times a constant, so that's where I get my 4bz. And then 13 times az would also give me z, so I write that. P and z, coefficients, p equals -3. Okay, you're starting to feel the rhythm here a little bit. And then I write z to the 0 just to remind you that that might be the constant. So the only way to get a constant on this particular setup is 13 times b, and that has to equal q. We know what b is. We get q equals 52. So we're done. We've got it. Part B says, hey, can you find this another way? And I think it's odd, but you got to know that it works. They're saying plug that 2 plus 3i or 2 minus 3i into the function and solve for pq. So I've done it real quick. Oh, you little sucker. Let's just do that. So part B, you just plug 2 minus 3i into the function. You got to do some multiplication. You know, you got to keep your ducks in a row. So when you multiply 2 minus 3i cubed, you get this. When you plug that in, you get all this. So then you have one complex number equal to 0. Well, comparing coefficients is really the idea, but here we are. We look at the real and the imaginary part. So the real part on the left side equals the real part on the right side. The imaginary part on the left side equals imaginary part on the right side. This one gives up p equals -3. Plug it in, and we get q equals 52. Wouldn't you say basically that that's the same way you get the same answers? So boom, you pick. All right, so I kind of did this one. You can check it out on your notes. I just wanted to make sure you understand purely imaginary. They're telling you you have a 0, a plus bi, but purely imaginary means it's just bi. But if bi is a root, isn't its complex conjugate negative bi? So right there is really important to kind of catch on to. So we know one linear factor, another linear factor. Since it's a cubic, I didn't use ax plus b here because I already used b, so I just used the next variable in line. I multiplied the first two together to get this, and I got this. And then, just like the other problem, comparing coefficients, you know, and it all falls into your lap. You can check out my work if you want. There's two more great examples. They're both on the self-tutor. So instead of taking time out of the video, if you need more examples, feel free to get those. Second section, this is the trick, man. This is such a trick. There's a lot of notation here. I would definitely make a note that this is the leading coefficient. Just to give you a little bit of perspective, and a sub n minus 1 is really just the next term. And then a sub 0 is the constant. So that's the constant term. Hey, this might help you a little bit if we looked at the quadratic. That is a polynomial. So I'm going to do this real quick. Well, let's say we have a polynomial. It has a leading coefficient, the next coefficient, and the constant. Let's say the zeros, I'm going to just tell you they're alpha and beta. Well, that means if I write it in factored form, look like this. If I multiplied it out, got things, put them together, and divided both sides by a, what do we end up with? We end up with this equal to this. Comparing coefficients, that means if we take x here, b over a equals that, and that boils down to that crazy formula. The leading coefficient right here and the next coefficient with a negative out front is always equal to the sum of the two roots. Cool. Over here, if we do if we're looking at the constant, we set c over a equal to alpha beta. So the product of the roots is always equal to the constant over the leading coefficient. All right. Well, I'm not going to do this start to finish with the cubic, but we set it up the same way. We divide both sides by a and we multiply this out. Okay, that's just a lot of work. It's just nothing, it's too hard. You can do it. But if you compare coefficients, then you see this is equal to this. So the negative goes out, and we get the exact same formula for the sum of roots. So maybe for 2 roots, 3 roots, n roots, the sum is always going to be the leading coefficient dividing into the next coefficient and always the negative. So that always is going to be true. I like negative b over a because it really kind of connects those first two instead of a sub n and a sub n minus 1. Totally up to you. This one though, the product changed. This negative came into it. So if you go back to the formula pages where they just give you the formula, they give you negative 1 to the n. So as n becomes positive, or even or odd, that's going to change that negative up front. So any even, it's going to be a positive, like the quadratic, 2 roots. There you go. And it's always going to be the constant term over the leading coefficient. The constant term over the leading coefficient. So I think they had a sub 0 over a sub n. So don't get nervous about what's a sub 0. Put it in the context of the problem. Leading coefficient and constant. So I don't know if I went backwards or forwards. When you're looking at a polynomial, these are the 3 things you need to pay attention to. Okay, there you go. Let's do a few problems. So we give you the roots. We tell you the leading coefficient. Find the sum and product of the zeros. There's no formula. They give you the roots. So, or the zeros. Just the sum, add them all up. The square root of 2's are going to cancel out. And the product, you're going to have to multiply some things out. In this case, very rare, they came out to be the same. So the coefficient of x squared, now that's kind of like, wow, that's messed up. But remember, this is a cubic. So they're really asking for the number, the next, that we have the leading coefficient. It's really the coefficient of the next value. So in part B, they're asking for this. Well, the sum of roots is going to be equal to that value over 2/3. So the sum of roots was 3. It's negative b over a, negative b over 2/3, and then we solve for b and we got negative 2. Okay, just multiply both sides by 2/3. And then the product of roots we know is also 3, and that's going to be the constant term over the leading term. The constant term, we don't know what that is. We have a cubic, so it's negative, and we get negative 2 again. Lucky. I know, I'm just talking at you. It's just, you got to know everything needs to fade away that's not important to bringing to the problem, and other things need to kind of step up. Number 5 is a good challenge, but I'm not going to do 5 because they did 5. If you need help, check out the self-tutor tutor on example 21, which I think is right there in the book. All right, now I have 2 more examples, and I want to make sure that I start them for you. So leading coefficient of 1 and a constant term of 25. So there's your 1 and there's your 25. Okay, so if you need that picture, you can. A sub 3, why do I put a sub 3? Because that's connected to the x cubed, but I see it as really my second coefficient. It's going to be part of the sum of roots. All right, so I do the sum. I get 2a plus 6. It's negative a over the leading coefficient 1. And then I kind of got stuck, and I was like, what? But instead of giving up, instead of crying really hard, I cried just a little bit, and I tried the product. I wondered if the product is something I could do. So I went to the product, I did the roots, I multiplied them, I got this stuff. I know it's equal to negative 1 to the 4th because it's a quartic, the constant over the leading coefficient, so that's 25. And I got this. I was like getting a little nervous. I got everything to one side, and I'm like, wait a minute. Mr. Sayers has told us we're going to kind of get these disguised quadratics. So I took a deep breath, and I factored that sucker. And since they're both the same, plus or minus 2, looked in the back of the book, of course, because I want to make sure that, yes, I got it right. All right, so 7. People wonder, what does it take to get a 7? Well, it means you just got to go fast and kind of know how to do these things more generally rather than get the number. So I thought 7 was a good one to talk to you about. When they say show, that means this is true and this is true. Don't plug them in and see if show it works. What they want you to do is get there, arrive there, and then hence use that to help you solve for what P, Q, and R might be. In other words, if you can't do this, you can still do this sometimes. So problem-solving techniques. Don't give up just because you couldn't do the first part. Use the result. Maybe you can do the second part. All right. So we're going to do the first part. It says show that those. I don't know even how to start, but guess what? This is some product of roots. They tell you something about the roots, so therefore I just start with something. All right. If I add them all up, it's going to be the second coefficient, negative of that over the leading coefficient. So I ended up with equal to P, and then I subtracted P. I got, hey, wait a minute. That is exactly what I wanted. Maybe this isn't so bad. I'll bet the product's going to do something. And sure enough, if you look at the product, you develop. Oh, that's so awesome. You develop this. So life's good. So maybe just starting, whether you don't see it or not, or haven't done that exact problem. It's important. So we go there now, and we know this is true. So how do we do this the next part? Well, I mess around with this a little bit, and I thought there would be a little bit more efficient way. I think this is the best way. I don't know another way, but I'm sure you guys are super smart and have a lot of time on your hands. You can try something. Be awesome. We know these are the roots. We know the polynomial is right here. I didn't rewrite it. I just wrote it as p of x. So I actually multiplied the left-hand side out. Now, some people just memorize that this is what you're going to get. I'm going to bring your attention. I actually already did this with showing you the sum and product of a cubic. I kind of jumped to it, and yeah, I kind of memorized that. I wanted to show you that there were like legit steps that get you there. You're welcome to go through that. I made one negative error. I had to find it, and I did. So now it's all about comparing coefficients. It's all about comparing coefficients. If you compare the x, you're going to get this equal to q. We make the substitutions. We get a quadratic. We get it equal to 0. We find that it's r equals 1 and r equals 0. Earlier in the problem, they said it couldn't be 0. So we are done. There you go. Thanks for playing today. I think it's going to go well for you. At least I hope it does. We'll see you.